So in direct current circuits, here is the question that we need to answer. You have a circuit with all these resistors, 10 ohms connected here. We have the 8 ohms and the 4 ohms connected in parallel with the 6 ohms in series to that. And then we have this 5 ohm resistor. And then the 9 volt battery has an internal resistance, 0.5 ohms. That internal resistance is just shown to be connected in series. So that's the circuit. And the question says a 9 volt battery whose internal resistance is connected in the circuit. A, how much current is drawn from the battery? So how much current starts off from here? B, what is the terminal voltage of the battery? Which means, what is the actual voltage available to the external circuit? So that's what you mean by terminal voltage. And C, what is the current in the 6 ohm resistor? So those are the questions. Let's get those answers. So first of all, we will have the 8 ohms and the 4 ohms that are connected in parallel. We will find its equivalent resistance by using the formula 1 by R is equal to 1 by R1 plus 1 by R2. But a shortcut to that is just to take the product divided by the sum. So it's 8 ohms and 4 ohms. Remember that? It's this 8 ohms and the 4 ohms. So it'll be 8 multiplied by 4 divided by 8 plus 4. So that's 32 by 12, and that gives 2.67 ohms. So those 8 and 4, both of those, can now be replaced with a single resistor, which is of value 2.67 ohms. And then when we look at that, we see that these two, 6 and 2.67, are in series. So you just need to add them both, and that could be replaced with 8.67. So there you have it, 8.67 ohms. And the next, we have the 10 and the 8.67 in parallel. And in order to replace that, again, use the product by sum, which would be 10 times 8.67 divided by 10 plus 8.67, right? So when you do that, you would get 4.64 ohms. 4.64 ohms. And so this is the final circuit that we have. And in the circuit now you have this 5, 4.64, and 0.5 ohm all connected in series. So just add those three up. You get the total resistance, and then 9 divided by that total resistance will give you the current. Okay, that's how we do this problem. So here it is, the 8 and the 4 ohms giving 2.67 ohms because the 8 and the 4 are connected in parallel. And then the 6 ohms and the 2.67, they are in series, so they give a total of 8.67 ohms. And the next, we have this 10 and the 8.67 in parallel. That gives 10 times 8.67 by 10 plus 8.67. That gives 4.64 ohms. So we have 4.64 ohms, the 5 ohm, and the 0.5 ohm connected in series. So the total is just the sum of all three. That gives 10.14 ohm. And then the current is 9 volt divided by that total resistance, which is 0.887 ampere. So the current that flows out of the battery is 0.887 ampere. All right, now let us look at the next question. The next question is, what is the terminal voltage of the battery? All right, so to find the terminal voltage of the battery, we'll have to go all the way here and we will find the voltage that's lost inside the battery. Remember, the battery has a resistance of 0.5 ohm. So this entire thing is the battery, and this is the internal resistance. So when the current of 0.887 ampere flows through the battery, that's going to produce a voltage of 0.4435 volt, correct? That's the voltage that's lost inside the battery. And therefore, the terminal voltage will be the 9 volt take away what is lost. So that's why we have the terminal voltage as 9 minus 0.4435 volt, which gives 8.5565 volt. So that's the terminal voltage. So the terminal voltage is always the EMF of the battery, which is 9 volt in this case, take away the lost volt. Okay, that's how we find the terminal voltage. And the last question is, what is the current in the 6 ohm resistor? So to find the current in the 6 ohm resistor, we just need to find the current in this branch, because that will be the same because they are in series. So let's get there. We know that when you add these two resistors, you get 8.67. So if we could find the current in 8.67 ohms, we will have the current through 6 ohms. You see how that works? And then let's find the current through 8.67 ohms by doing this. We know that the current that's flowing through this 4.64 ohms is 0.887 ampere, right? We know that's a current flowing through all of these. So we know the current through this is 0.887 ampere. So if you multiply that with 4.64, you're going to get the voltage here, the voltage across 4.64 ohms. Is that right? Once you have the voltage across that, we can find the current, because now we know that the voltage across these two should be the same, because these were the two that produced 4.64. So now we know the voltage here, and if we divide that voltage by 8.67, we will get the current. So that's what I've done here. The voltage divided by 8.67 gives approximately 0.475 ampere. So that is what I've done, okay? And we can check this out. We can check this out on the circuit here. We can actually check it out. Let's see that. So here it is. The current through the 6 ohms is 475.339 milliampere, which is 0.475 ampere. Of course, the current through this will also be the same. And that's why we found the current through 8.67, which is the combination of the two. So I hope you understood how that worked. We first found the voltage and then divided the voltage by the current, by the resistance, to find the current. So that's how this problem is worked out. Thank you. So here is a circuit, rather complicated. So you have the 30 ohms, you have a 40 ohms here, a 1 ohm, a battery of 45 volt, a 20 ohm resistance, and a battery of 80 volt, and its internal resistance is 1 ohm. And in this circuit, we are asked to calculate the currents I1, I2, and I3. So we got to get I1, I2, and I3. So first of all, when you look at the circuit, and apply Kirchhoff's junction rule, we see that current I3 is flowing into the junction while currents I1 and I2 are flowing away. So that means I3 is equal to I1 plus I2 because what comes in should go out. So that's the first thing. And then we will apply Kirchhoff's loop rule in the top loop, which is here. We will apply it in the top loop and then also in the bottom loop. And then we will solve those two equations. Okay, that's what we're going to do in order to solve this problem. So here I have the equations. Let's apply Kirchhoff's loop rule to the top mesh, and you would see that we are going in the direction of the current, so that is 30 I1, and then you hit the negative, so it's negative 45, and then you have these two together adding up to 41 ohms, and we are going in the direction of the current, I3, so it'll be 41 times I3 is equal to 0. Let me say that again. So we go this way, we are flowing in the direction of the current, so the product is 30 times I1 minus 45 because we hit the negative, plus 41 I3 is equal to 0. And then we can do the same thing, apply Kirchhoff's loop rule in the bottom mesh, and we will see that if we start from here, okay, so we get negative 80 because you're going to hit the negative 80, right? Let's see if we can start from here, okay? So it's negative 45, 41 I3, that's plus 41 I3, and then come down, negative 80, because we come to the negative terminal, and then you have 20 plus 1, 21 I2. So again, plus 21 I2 is equal to 0. So that's what I've written here, 21 I2. But you remember I3 is I1 plus I2. So I2 can be written as I3 minus I1. So I'm going to substitute for this I2 as I3 minus I1. Right? And then distribute this. All right, so that's the next term. You have 21I3, negative 21I1. And then we combine this 21I3 with 41I3 to give us 62I3. And we also combine negative 80 and negative 45 to give negative 125. So here is the next equation that we get. So now we have two equations, simultaneous equations that have variables I1 and I3, and we need to solve those. Now in order to solve that, what I've done is I've used the elimination method. I multiplied this equation with 30 divided by 21 because I know when I do that, this will become negative 30 I1. So that'll get cancelled with 30 I1. Right? Negative 30 I1, a positive 30 I1 will get cancelled when I add the two equations. And so I need to multiply this number also with 30 divided by 21 and then add it to that, to 45, and I get 223.57. Similarly, when I do this 62I3 multiply by 30 by 21 and added to this, I get 129.57 I3. Rearrange that and solve. I get I3 is 1.73 ampere. Once I get the value of I3, I just substituted the value of I3 into this equation here, which you can see, and then calculated I1. I get I1 as 0.86 ampere. 0.86 ampere. Now, because I know I3 and I1, I can now calculate I2, because I2 is I3 minus I1, and that gives me 2.59 ampere. So that's how the currents are solved. You need to take a look at this and understand how it's done. It's the application of Kirchhoff's junction rule and the loop rule. Okay, that's how you solve this equation. So here we have the simulator, and let's see if we get the same currents. Okay, there's obviously going to be some understanding here. So let's get that. So this is the same circuit, as you can see, the 80 volt, the 45 volt, and all that. Those resistances are exactly the same. Let's find out the currents. First of all, do you notice that the current I1 is flowing down? As you can see, it's not flowing up as shown in the diagram. So that's why, excuse me, when we find the current I1, we get 0.858 ampere, 0.86 ampere. But when we actually calculated, we got it as negative. You know why? Because we were showing the current flowing up, while actually the current is flowing down. That's why we got negative 0.86 ampere. Now, I3 was 1.73 ampere. That was in the same assumed direction, 1.73. And I2, we got 2.58 ampere, roughly. There are a little approximations. So that's how we apply Kirchhoff's laws. So I hope the simulation adds to your understanding. We can in fact find the voltages at each point, but in this case it's enough to show that the currents here are the same, 2.58, 2.58, 2.58. The current here, 1.73, again 1.73, same branch. Here it's 0.85 ampere, again 0.85 ampere. So I hope you understand how we applied Kirchhoff's laws to break this complicated circuit down and to calculate the currents that flow through each resistance. Thank you.